Hi, Grace.
Try to hold on through next spring, and then
how's it going?
After they've already had your financial aid locked up and they can't do anything to it, that's whenever you drop it and transfer it. They can't do anything.
I'm not transferring. It's not like.
Well, you know what I mean, though. You're gonna go to watch you, and then you'll get your math degree without having.
Everybody get their homework in?
Oh shit!
No.
That'd probably be the easiest way to deal with it and still get everything out of the honest program you can.
Well, I just want to take one more. I just want to take one more class without having to take the class.
Right.
So I'm gonna see if I can talk to him and see if I can just take the. I don't care if I graduate from getting out. My legs is two shits. It was more than that.
Thank you. Questions about anything before we get going here?
Oh, the nose. I'd probably need another way to screw milk over, which is would be nice to see somebody maybe manage to do at some point.
Did I just hear a whimper?
We have homework already?
Oh, Joe! Wait, what is up, dude?
What?
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 You know what? Don't act like you're innocent here. When's the test, Dr. Joe?
The 19th?
And next week or weekend?
The weekend.
Okay, never mind.
Is today the 6th? No.
Yes.
Dude, you got a lot going on here.
Wait, this is a lot.
There's 9 problems.
That's a lot.
Huh? Yes.
See, when I get 9 problems in calculus, it's not a big deal. But when I get 9 problems in here, that's a lot. Dr. Joe, when you say we only have 9 problems, it sounds like it's not that bad.
That's right. It's not that bad. Exactly. It's not that bad. See?
No, it's really bad.
Goodness gracious.
Complain.
Really? That never happens with you, Michael. It's so out of character for you.
So, clarification question.
Okay.
The 4.1 and 4.2 are from the book.
Correct.
And then what is the 11s from? The 11.8.
The packet. Did you get a packet?
You should have. I gave you a secret yesterday.
You were here, right?
Look.
Do I need a packet?
Yeah, I'll send one. They'll send me time.
Oh, Jesus,
I'm sure it's in there somewhere, but
There we go.
thank you. Oh yeah, I do have this.
Oh, shit. Wait,
Seriously, I think it's in my theory of interest notebook.
With 11 and 8 in it?
Yes.
Oh, okay.
Yep. I gave you another packet too, right? With 13 and 15. I gave that last time too. Yeah.
Yeah. Is that in this? What is the packet look like?
Definitely.
It's a packet.
Yeah,
Problem said 8 isn't the same one with 11.
Oh,
definitely ended up in my theory.
It's towards the back.
we did it last time. Yeah.
Yep.
Okay.
Wait, what?
Let's see if we can do 36 here. This would be out of the problem set 8 as well. So we did a marginal distribution at the end of class last time. The marginal distribution, and we'll do another one here in a minute as well for continuous distribution. Sorry.
Just being sick.
It's just phlegm. We'll do another one here in a minute that is continuous as well. But I wanted to do an example here where the joint probability the joint probability mass function actually is a mass function for a discrete distribution rather than a continuous one, and show that it works the same way. So we want to do the marginal probability for x. Remember, when we do the marginal probability functions, is when we do the adding up over all of the possible values for the other variable. So when we do the marginal probability function for x, if we're adding up or integrating over all of the possible y's, there shouldn't be any y's left at all. The thing that should be left is the PMF or PDF for x. We're done. Okay. So in this case, they've actually got it listed out for what the values for x are. So it's just a matter of figuring these things out. if we add these up over all of the y's and look at the probabilities, so the idea here would be that we want to sum this, if we want to do the marginal for x, so our PDF for x, we're going to sum this up over all the y's for our P of xy. Looks a little bit weird, right? That's why and this is why our marginal distribution looks like a piecewise defined function here. Now there's one of these that you should be able to throw out without any issues, without even working the problem. When we're done with this, we have to get a PDF for x, which means that the only thing that we should have left are x values. Looking at our support for the joint PMF, what are your only possibilities for x? 0 and 1, right? So which of the potential marginal PMFs that they have gets thrown out immediately? D, right? Right? It says 1, 2, 3 for x. We don't have that, correct? In fact, my guess is that's probably the joint, or excuse me, that's probably the marginal for y. Doing the wrong one. If you did the marginal for y, I'm guessing you'll get D, with just y equals 1, y equals 2, y equals 3. Okay? Okay, so let's just see what happens when we do this. Pardon me. So this says we want what this says is that when I plug a number in for x, the value that should come out is that value for x plugged in and then sum it up over all the y's. So for us, we know that one of the values that we can plug in for x is 0, right? That's one of our possibilities for the x. So this would say sum it up over all of the y's, plugging in 0 for the x, and then just taking all the y's and plugging in all the possibilities. Okay? So if I go up here, what are your possibilities for y here if x has to be 0? 1 and 2, right? So this would be P of 0, 1 plus P of 0, 2. That's all we're doing for that. If I put in 0, 1 for P, looking at the very top of the screen, if I put in 0, 1 for P, what do we get? 1/12. And if I put in 0, 2, 1/6. So this will add up to a 4th. Yep. So right away, I think we're done. What does the answer have to be?
Hey.
Really? Good reading today, Michael. Has to be B, doesn't it? It's the only one that we have. But let's make sure that we understand how to get the other one. So if we want f of 1, again, this is a sum over all the y's, p of 1y, right? If x is 1, what are your possibilities for y? Yeah, the 1, 2, and 1, 3, right? So this will be p of 1, 2 plus p of 1, 3. Those, and really, I mean, we're doing all the y's possible are fine, but these are the only y's that have non-zero probabilities with an x of 1, right? I mean, you could do 0, 3, it just would be 0, because we don't have that one defined at all. Okay? So, if you put in 1, 2, 1 for x, 2 for y, we get 1/3. And if we put in 1 for x, 3 for y, 5/12. And that better be 3/4. You get 9/12. When you add that together, you get 3/4. So we really do see we get B better. And the other reason why I went through this, besides just practice, I really do see this as a PDF, right? These are the only possibilities for x. It's x is 0 or x is 1. And when I take all of the probabilities and add them together, I get 1. So I really do get a PDF for x. Does that make sense? Okay. Let's see if we can do another marginal here. Do a few of these, make sure that we're all on the same page with these. So this one I wanted to do, yeah, because I already did that one. All right, so this one says find the marginal for y rather than for x. This one's continuous because it's giving us intervals for the x and the y. Now we have to be a little bit careful when we do this, because when I find the marginal density function for y, I've got to integrate this over all of the x's, right? But notice that this is not a rectangular region. I've got x's and y's that are related to each other in some way. So let's draw the picture here. Our x's go from 1 to 3, and the y's go from x to 2 plus x, so I better make this a little bit bigger. So y equals x is that line. Y equals 2 plus x is that line. X equal to 1 is here. X equal to 3 is here. So it's this region in here that we're looking at.
So how do you know you have to integrate on these versus like this one?
Because this one's continuous, because it says x is less than, or 1 is less than x is less than 3.
Okay.
Yeah. That's okay? How to get the which lines?
Is that just y equals x?
That's y equals x and y equals 2 plus x, yeah. I just made them up.
Just pull them out my ass.
Yeah, pretty much. That's how it goes. All right. So, what's that?
It'd be like that sometimes.
All right. So when we do these, when we do the marginal for y, I have to do the integral over all of the x's. If I'm doing that's like if we had a double integral, the x integral would be the one on the inside that we're doing. So we're treating y like it's a constant. So in this particular one then, it makes it a little bit more complicated because notice that if I'm down here holding y constant, I've got different bounding curves than if I'm up here. Right? Okay? So this is going to be, when we do the marginal for y then, bless you, this tells me I'm going to have to be a piecewise defined function because it depends on where the y is. Right? If the y is between 1 and 3, then I'm going to integrate from x equals 1 to x equals y. Right? Thank you. Those are my left and my right bounding curves. But if y is from 3 to 5, I'm going to integrate from y to 5, or excuse me, y to 3. Okay? So we've got two different things that we have to worry about for this particular problem. So 1 less than y less than 3 will have what? Our left bounding curve is 1. Our right bounding curve is x equals y. Now remember, if I'm finding the marginal for y, every single reference to x has to go away. Many of you are in Calc 3 or had Calc 3, right? Remember that when you do double integrals or triple integrals, or how many other integrals you're going to do, when you integrate with respect to that variable, there's no more reference to that variable left. It has to be gone, right? Which is why your outside integral always has to be constants. The limits of integration always have to be constant, right? The variable cannot be left once you've integrated with respect to it. Okay? So when we do these, when it says marginal density function for y, absolutely everything that's left has to be in terms of y. No x's. Okay? So when I do this integral, my bounds have to be x's. In terms of y. X's in terms of y. Right? Okay? So from 1 to 3 again, left x is 1, right x is y. Now we're just going to integrate the PDF, which in this case is 1/4 dx, the joint PDF I should say.
Dr. Joe?
Yeah.
Why don't we just integrate with respect to y first?
Because we're looking for the marginal with respect to y.
Yep.
That okay so far? You okay? Yep, okay. So this becomes what? 1/4 x evaluated from 1 to y, so that we just get 1/4 y minus 1. Not 1/4 y minus 1. Well, if I factor out the 1/4 it is. I'll just cheat. It's fine. This okay? And if we do the other one, what will the other integral look like from 3 to 5? Y to 3, because it's x's. Okay, 1/4 dx. So we'll get the same kind of thing. We'll get 1/4 times 3 minus y. It's a y down there.
Can you say how you got y to 3 one more time?
Which one?
Instead of the integral
Oh, it shouldn't be y to 3. It should be y.
to, yeah.
Y should be y what?
minus 2?
It should be y minus 2. Good.
Okay, cool.
Yep. So this should then be 5 minus y here. Let me simplify. You're right. Good catch. Because I have to have that line in terms of y, not in terms of x, right? This line here, this line is y equals x plus 2, but we need an x bound, right? So we have to change it to x equals y minus 2. And the 5 comes from the fact that I'll be doing a 3 minus a minus 2. So our marginal for y is a piecewise defined function. It'll be 1/4 of y minus 1 if y is between 1 and 3. And it'll be 1/4 of 5 minus y if y is between 3 and 5. And it's 0, of course, otherwise. That one was a little bit more complicated, and would it have been even more complicated had these 2 points here not been on the same horizontal line, right? Had that been even more slanted, you would have to do 3 integrals instead of 2. You see what I'm saying? If it had been even more slanted, more twisted, because I would have had vertical line to right line, left line to right line, left line to vertical line. I would have had 3 regions instead of 2. Okay, do you have a question?
Yeah, so how do we know when it's asking us to find the PDF, or when it's asking us to find, like in the last one,
I guess it was asking us to find it.
Yeah, it was fast to find it. Both of them were asking us for the PDF, yeah.
Okay.
It's just when they say marginal, they mean that you're starting with a joint one and recovering the PDF or a single one from the joint. It's just a fancy way to say find the PDF. Yeah, Megan.
To get the 3 and 5
Mhm.
for the Y, is that because like the second line goes from 3 to 5?
Yep, because we're going from that horizontal line here up to there. That's where the 3 to 5 is coming from.
And that's on the Y.
It's on the Y values, right? Because everything, when we're done with the find the marginal, everything has to be in terms of Y. Yep. And they all have to be when we're talking about the bounds, they have to be constants too. See if we can do one that's a little less ugly, hopefully. Let's try this one. This is 13.3. I did give you all 13s last time, right? I gave you 2 packets last time? Kevin, you made me one. Welcome. I think this one's a little bit more straightforward. Let's say hope so. See if you can figure it out. Ooh, it's still green.
Is this one fully X constant?
This one is, we're doing the marginal density for Y, so we want to hold the X constant. Or, sorry, the Y constant. We want to integrate over the X's.
Why is the top part shaded and not the bottom?
I don't know, why?
I don't know. I'm asking you.
I'm asking you. You tell me why the top started shading.
But I asked you first.
I know you did.
That's true.
But I'm the teacher.
Because I thought X had to be. Older than your Because X has to be. What? Why can't it be less than X? Square root Y.
Correct.
Well, I screwed that up.
Yeah, so if you're finding the marginal for Y, we're going this way, right? Holding the Y constant, integrating the X's essentially. So if you do the marginal for Y, and I don't think necessarily think our textbook does, but a lot of books will use the F for the X and the G for the Y. why I've been writing the marginal as G. Another way you might see this is since this is f of xy, you might see f sub y of xy, or f sub y of y. It's another notation I might use. It's a function of just y is the important part. All right, how do we calculate this? Yeah, integral 0 to root y. Okay. dx. Right. Antiderivative is okay. 2y. For what values for y, by the way? What are your only y's that you can plug into this to make any sense? 0 to 1. Good. Oops. Yeah, Katie.
So let me say this question. How do we know that we graph the root y and not the line y equals x?
Because of the root in there. The way I thought about it was I just squared both sides of it and made it y equals x squared. And then just read that part of the parabola. It's literally because of the fact that basically the way you're getting this boundary line is by thinking of this as an equation and graphing the equation. Graph the equation x equals square root of y.
So it's not like, because originally when I drew it, I drew y equals x and y equals root y, or y equals x squared. Sorry.
Oh, it's because there's not another relationship between x and y. If you wanted what you said, you would have had it would have had to look like this. And then I've got two equations essentially. So this is only had the one equation, if you will.
Yeah.
That's why it's just the one bounding curve. And the other ones are the vertical and the horizontal lines that bound the region.
Gotcha.
This one okay?
So.
So our zero, y is from 0 to 1 because that's just what's in the.
Yeah, I mean, there's a couple of ways to think about it. That was the way the region looks. But in the formula, if I have 0 is less than root y is less than 1, and I square everything, I get between 0 and 1. So you see it from the algebra or the geometry.
Okay, so for like, so we're just holding the opposite constant.
Yep. Well, no, in this case, we're holding the y constant integrating over the x's, right? And that's what we're holding.
We're holding whatever's told.
Yes. Yeah. That's correct. All right. Let's look at this one. This one's out of your textbook, even though that last part's a little bit hard to read. What I'm interested in... That's not the one I wanted to do. Sorry. Even though I labeled it, I picked the wrong one. Hold on. What do I want to do?
Haley would be very disappointed.
Haley's always very disappointed in me. It's fine.
She's just a disappointed person.
Oh shoot, maybe I didn't copy the one I wanted. Hold on. Sorry, I made a copy of that one, but I want to do that one later. What's that?
She was like, Haley was telling me how she had like an in-person interview
Oh yeah,
today.
yeah, yeah. It's in Boston.
After
Yeah.
having a call interview yesterday,
Yes. Yep.
and she was all worried about it, and I was like, well, I would take that as something good. Like, they obviously thought you showed yourself very well.
Oh yeah, absolutely.
So.
It's definitely a positive thing. This is 4.1-11. Oops. No, I forgot a 2. All right. Apparently I forgot to make a copy of that particular problem because I wanted to put it in here. Okay, so the joint PDF is f of xy equals 2e to the minus x minus y, and then they give you the region that we're integrating over. Well, let's first look at the PDF, and we're gonna do the marginal PDFs here in a second. But let's just look at the joint PDF to start with. Can I break this PDF up into a piece that only has x's and a piece that only has y's. Okay, I write it as the product of two functions, one that just only has an x in it and one that only has a y in it. I probably wouldn't ask if the answer were yes, right? If I specifically went and grabbed this particular problem, right?
It'd be funny if you did.
All right, how can I rewrite this as a product of function only of x times function only of y? Yeah, break the exponential up, right? Because I can think about it as just adding a negative y, right? And when we add exponents, we must have multiplied. So this is 2e to the minus x, e to the minus y, right? Okay. So I really do have function of just an x, function of just a y. So we've talked about and probabilities in the past. And we also talked about the idea of independence in the past, right? That if x and y, if the two events are independent, we can just do the probability of the one, probability of the other, and multiply them together. Right? So if we think about this being broken into two pieces, this kind of looks like we can do that, right? This is, it's not, because there's a catch. So don't write down what I'm saying and thinking, oh yeah, they're going to be independent, because they're not in this case. And I'll tell you why. Okay? But it kind of looks like that's what we have, doesn't it? I've got, this thing should be telling me, or at least the e to the minus x part, should be telling me something about the probability with respect to x, with no regard to y, right? And the same idea here, y with no regard to x, and we're multiplying. Right? And this is something that we need in order for things to be independent. Okay? I need information about x independent of information about y, and vice versa. I need to be able to split up this joint PDF idea into two pieces like this. The problem with these not being independent actually has to do with the region that we're in, that the support is in. The way that the region is written, is it possible for x and y to be independent? For example, if y is 5, can x be whatever it wants? No, right? Or if x is 3, can y be whatever it wants? No. Okay, so in order, the first thing that you look for variables to be independent of each other is that the region has to be rectangular. If it's not rectangular, then they can't be independent. Because what happens if it's not rectangular? Then it depends where you are in the region for the allowable values of the other variable. Right? In that previous example, when we had that parabola, it mattered where you were for what the y's could be, or what the x's could be. So they couldn't possibly be independent. Now the way that you can check that is with the following. So let's let, I'll say f of x, y be the joint PDF, or PMF, either way. I'm just going to say PDF of x and y. And let, I'm going to say f1 of x, just to match what the textbook says, be the marginal PDF of x, and f2 of y be the marginal PDF of y. I'm only using f1 and f2 as the marginals because that's what your book uses. Okay. Then x and y are independent. Oops. If f of x, y is equal to f1 of x times f2 of y for appropriate x's and y's in the support. But this is where the be careful part is. It looks like the definition says that as long as I can break my joint PDF up into two pieces, then they're independent. And that's not what it says. Okay? It says that if I can write my joint PDF as the product of the marginals, then they're independent. So what this tells me about this original problem where I said we could split it into two, it tells me those aren't the marginals. It tells me that e to the minus x and e to the minus y are not the marginal distributions here. Okay? Because it looks like I've got it broken into two pieces, right? But we already agreed that they can't possibly be independent because the allowable values for x depend on the y and vice versa. So they can't be independent. Okay. So this is where I wanted to do this specific problem because it's a be careful idea. Okay? Much like what you do probably have done in your Calc 3 and some in Calc 2. If you've got a rectangle that you're integrating over for double integrals, and you can break your x's and y's independently, you can just completely split apart the two integrals and do them independently. Right? It's the same concept. If one of them involves a variable, I can't completely pull the one outside of the other. Right? What I mean by that is there's a difference between, I'm going to write this on the board. If you think about it in terms of the double integrals, if you had something like integral from 0 to 1, integral from 0 to 2 of x, y, dy, dx, that certainly is this times that, because one integral doesn't depend on the other, right? But I have something like this, then I can move this y to here, right? Because that says integrate with respect to x first, right? But notice that I can't take, so you can get to here, right? But I can't take this thing and move it out. Why can't I take that and move it all the way out in front? Because there's a y in there that has to be integrated. Right? So I can't pull them completely apart. Okay? The only reason why I'm writing it this way is because you've seen this kind of idea in Calc 2 or Calc 3 with doing double integrals, right? You can split them apart if you've got constants on both of them, and I can split the variables from each other. Right? But I can't do that in the second case. It's the same idea here. It looks like I can factor it, but I can't split them apart from each other because the x and the y depend on each other for the region. That's what's happening in that double integral, isn't it? The x and y depend on each other in the region. Same concept. Okay? So the way we would check this in this case, if I look at my region, it says your y has to be greater than or equal to your x is the way it was set up. So we're talking about this region up here. Right? So if you wanted your marginals, so say I wanted a marginal for my x, if you wanted your f1 of x, what do your y's run through? Where do they start? At x and go off to infinity. Right? And then this would be minus 2e to the minus x, e to the minus y, evaluated from x to infinity for your y's. And you get 2e to the negative 2x if you simplify. Right? Because when we put it in infinity, we'll go to 0 still. For a given x, that will go to 0. And when we put in x, we'll have 2e to the minus x, e to the minus x, so you get e to the minus 2x for that. And you can probably guess that when you do this for y, you're going to get the exact same thing, just with a y instead of an x. Right? Because if I do it, well, yeah, it should be the same. Well, no, not quite the exact same thing, because your y's go this way, don't they? So what will your limits look like for that? 0 to x. So you'll get, actually you'll get what? You'll get 2e to the minus y minus 2e to the, oops, this should be a y. Yeah, sorry. This should be a y. 2y. What's that? You keep lying, I know. It goes from 0 to y. Yeah. Oh, that's okay. I should be catching it too. Notice now, if you take those two marginals and multiply them together, you don't get anything close to what the joint PMF was. Right? That's the reason why I wanted to do this particular example to talk about independence. Okay? You usually think of independence as, when I look at the probabilities, one probability has nothing to do with the other. So you might be thinking, when I look at the joint PMF, I can take one with the x, one with the y, and just multiply them together. But it's more than that. I have to worry about the region too. Okay, that's why I wanted to do that for this case. Because clearly now when I've got the marginals, if I multiply them together, I don't get the PMF again. The joint PMF back, right? Hopefully it's pretty clear if I take those two things and multiply them together, I don't get the joint PMF, right? Okay. So that was the point of why I wanted to do this particular one to introduce independence. Independence is great if you have it, right? You can just multiply together and call it good. But not in general, we don't have that. So one of the things that we're going to talk about in the next section, which I'm going to go ahead and go on to, is the idea of how do we calculate the idea behind being able to get a relationship between the x and y. What happens if they're not independent? And that's the idea of covariance. So I want to look at this 15.5 to start with. And we'll motivate a little bit later why we want this particular quantity for the covariance. It's going to look weird to start with, but this is why we want this quantity. So the covariance of x and y is defined as the expected value of the product of x and y minus the product of the expected values. It looks a little strange of why we want that particular quantity. Like I said, we'll talk on Friday about why this is what we want for the covariance, why it's this specific number. But if we can talk about it a little bit intuitively of why we call it covariance. Okay, co-2 idea, right? I have x and y together. I want to try to find the variance. Well, remember how we calculate variance of a single variable? What do you calculate? The expected value of x squared minus the expected value of x squared, right? Or x times x, expected value, and then expected value of x times the expected value of x, right? What does it look like we're doing here? Well, instead of x times x, we've got x times y. And instead of x times x, we have x times y. So we're commingling them. Okay. Now again, I'm going to give you a better mathematical reason why we calculate it this way. Okay? But at least it gives you an idea of what we're doing, right? We're trying to mingle the two together. All right. So when we do this now, let's do it for this specific example. I wrote over the top of it. But let's do it for this specific example where we've got these values. I've only got 6 values to calculate. I want the expected value of the product of x and y, and then the product of the expected values of x and y. So let's calculate those 3 things. If I want expected value of x, what do I need to calculate? How do I find that?
Assuming the top is x, the bottom or the side is y.
Yes.
So do we just take the x values when it's 0 and add them up?
So we'll take the, not just with the zeros, but we'll want to do expected values, right? So what do we do? Take the probability associated with that and multiply it by that number, right? And that one and then that one, right? So the expected value of x, well, your possibilities for x are -1, 0, and 1, right? Those are your possibilities for x. What's the probability that x is 0? Or sorry, what's the probability that x is -1? Sorry, let's start left. Let's go left to right like a normal person. What's the probability that x is -1? Yeah, 0.2. Why is it 0.2? You add them together here, right? So I'll write, just to emphasize, I'll write it as adding them together. What's the probability that x is 0? The probability that x is 0. 0.4. And the probability that x is 1, also 0.4. Everybody agree with that? So we get 0.4 minus 0.2 gives us 0.2. How about for expected value of y? What are your possibilities for y? 0 and 1. And I'm not going to show the additions here, but what's the probability that x, or excuse me, try that again. What's the probability that y is 0? 0.4. And the probability that y is 1? 0.6. And again, we just get those by adding across the rows, correct? In particular, we've essentially found the marginal distributions, didn't we? The marginal for x would be 0.2 when x is -1. 0.4 when x is 0, 0.4 when x is 1. The marginal for y would be 0.4 when y is 0, 0.6 when y is 1. And so this gives us 0.6, right? We also need expected value of xy, the product of the two. Okay. So notice that there's a lot of products that give you 0, aren't there? If I take this y value, the product of x and y is 0, isn't it? If I take this x value, the product of x and y is 0, isn't it? So the only things I really have to worry about are that one and that one. We agree? Because 0 times the probability is still 0, isn't it? So I don't need to worry about those for this calculation. What is the product for that first probability? That probability that's a 0.1, what is the product? -1, right? So it's -1 times 0.1. What is the product for the 0.2? The 1 times the 0.2, good. And then we get 0.1. So we're doing the expected value of x times y. So we're doing x value times y value. If x is 0 or y is 0, that value is 0. So I didn't even bother with those. I mean, there is, in here, there's a 0 times 0.7. Because that product is 0 at 0.1, 0.1, 0.2, and 0.3. The ones that I crossed out. Does that make sense? Yeah. Okay. And then our covariance here is 0.1 minus 0.2 times 0.6. Which gives us negative 0.02. So yes, your covariance can be negative, without any doubt. What the negative tells you means that there's a negative relationship between x and y. Basically what that means is that overall, not very much because it's a small covariance, but overall, as x gets bigger, the y gets smaller. That's what that tells you. As x gets bigger, the y gets smaller. Look at your PMF here. As the x gets bigger, values the y gets smaller values. So as your x, well, that's what it should say. As the x gets bigger, the y gets smaller, vice versa. Kind of looks the opposite of that, doesn't it? A little bit. Well, that's what it means, because we're going to talk about why that's true, because we're going to do least squares next time. But that's the idea behind the covariance, but I'm not seeing that from the PMF, because when my x gets bigger... Oh, yeah, that makes sense, I think. Oh, anyway, we'll talk a little bit more about it. You can see it a little bit nicer when I have better graphs of it. So, anyway, we'll talk about this more next time. Do some more calculations of covariance. Talk a little bit about correlation and least squares next time as well. So, we'll see you Friday.